Welcome back all of you. So we have completed the load flow analysis using Gauss-Seidel method. We have discussed the different steps, the problem solving as well as the flow chart also. Okay. Now the next method that is in our scope, in our syllabus is Newton-Raphson method of load flow analysis. So in this lecture, we will be discussing much more on the mathematical background and the basic concepts of Newton-Raphson method, fast decoupled load flow method and load flow method.
Now the next method in our syllabus is Newton-Raphson method. This method we might have studied in mathematics. It is just a simple extension of those methods applied in power system. Before proceeding to the numericals or flowchart or algorithm, let us understand what is a mathematical background in Newton-Raphson method. This method is quite easy compared to Gauss-Seidel method. So many steps are also involved here, but it is quite easy and error-free compared to Gauss-Seidel method. Now let's analyze what is the mathematical background of Newton-Raphson method or NR method. Now in power system point of view, we know that the complex power SI, S represents complex power. Complex power SI, or rather our parent power SI, where this I represents bus number. SI means apparent power of ith bus is equal to Pi plus JQi, where P represents active power and Q represents reactive power. Pi means active power of ith bus and Qi means reactive power of ith bus. We have also seen that the complex power is equal to Vi into II conjugate, which means the complex power of ith bus is the product of voltage of that particular bus and the conjugate of current of that particular bus. Okay. Now, the current injected to any bus will be equal to sum of current to that particular bus, isn't it? If there is a particular bus here and here current is coming and here another and here there yet another. Here there is one current, here one current is entering and here one current is leaving. So what is the total current of this particular bus? Total current will be this current plus this current minus this current, or rather we can say the current of a particular bus will be the sum of current injected to that particular bus. Okay, and a current I is equal to injected current is equal to voltage divided by impedance, or voltage into admittance. Okay, so a current of a particular bus I will be equal to voltage of that particular bus I into this bus admittance matrix or that particular element I. Okay, keeping this into consideration, I can write the injected current is the sum of all the currents to that particular bus, that is Q is equal to 1 to N, where N represents the total number of buses in the system. Okay, so that's it. I means the ith bus and N represent total number of buses in the system. Now, so far in the Gauss-Seidel method, we have been evaluating or analyzing everything by considering all the parameters in rectangular coordinates or rectangular form. But in the Newton-Raphson method, it would be much more easier if we are converting this rectangular form into polar form. So, a particular admittance will be having a magnitude and an angle. The angle of the admittance is usually represented by theta. So YIQ, because we usually represent the admittance like Y11, Y12 like that. So generally I can write it as YIQ is equal to magnitude of that admittance and angle of that admittance. Magnitude with this modulus, and the angle is represented by theta. Remember, angle of admittance is represented by theta. Now VQ simply represent voltage of the qth burst, which can be represented as magnitude of the voltage and angle of the voltage. Angle of the voltage is represented by delta. Now VI represent voltage of the ith burst. Again it is represented as the magnitude and the angle. Magnitude as modulus VI and the angle delta I. So remember, in this so far in this discussion, you have to keep in mind that angle of the admittance is represented by theta and angles of the voltages are represented by delta. So is that, I hope this much clear to you, the basic concepts. Now we can write that the complex power is equal to Pi plus jQi. We have seen this, which is again is equal to Vi into Ii conjugate. Okay, or I can equate this much. P plus jQi is equal to Vi into Ii conjugate. Okay, so now we are going to substitute all the magnitudes and angle here. So instead of Vi, I can write it as Vi magnitude and its angle. Now instead of this current, I can write like this, isn't it? Q is equal to 1 to n YIQ VQ, the conjugate. So now how will be writing this admittance? Admittance again can be written as with magnitude and with angle. Now why is this negative sign given to this angle? Because conjugate is there. Conjugate of theta angle theta is minus theta. Okay, so here it becomes minus theta IQ, and V, voltage of the qth burst, can be written as magnitude VQ and its angle. Again its angle also given negative sign because of this conjugate. Now considering or clubbing all these angles together, I can write it as magnitude Vi, sigma q is equal to 1 to n, this YIQ, then this VQ, then how many angles here? Delta I is there, theta IQ is there, minus delta Q is there. Clubbing all together, you can write the angle as delta I minus delta Q minus theta IQ. So what was our left hand side? Our left hand side was Pi plus jQi is equal to this equation. So you can say that Pi is the real part of the equation and Qi is the imaginary part of the equation. So this is our equation, and how will you separate real and reactive part of a particular equation, like R angle theta. If you got an equation like R angle theta, what is its real part? What is its reactive part? The real part is R cos theta. This is the real part, and imaginary part becomes what? Sin theta. So likewise we have written real part of the equation is the same equation with cosine of that angle. That is our real part. And our imaginary part is the same equation with sine of the angle. So you have separated or segregated out the real part and the imaginary part. So what is the real part? Is the active power. What is the imaginary part? It is a reactive power. So active power is equal to Vi, YIQ, VQ. Okay. In between you have a sigma. Q is equal to 1 to n. Cosine of delta I minus delta Q minus theta IQ. Clear? Similarly, our reactive power is equal to the sinusoidal of that particular equation. Now just observe these two equations, the active power and the reactive power. You can say that the active power mainly depends upon what all parameters. It depends upon admittance, that is true, but is the admittance variable? No, the admittance is usually not variable of a particular system. It is a constant. And which are the variable parameters here? The voltage is Vi, this voltage VQ, then angle of the voltage delta I, delta Q, and And does it depends upon theta IQ? No, because theta IQ is the angle of the admittance. Admittance is a constant, so theta IQ is also a constant. So you can see that your active power mainly depends upon the voltage's magnitude and the angles. Similarly, your reactive power also depends upon the magnitude of the voltages and its angle. Or you can say that your active power is a function of voltage magnitude and its angle. Your reactive power is also a function of function of the magnitude of the voltage and its angle. So you can write that your active power Pi is a function of magnitude of the voltage and its angle delta. Similarly, reactive power is a function of the magnitude of the voltage and its angle delta. So far is the concept of power system. Now we are going to introduce our mathematical background into this concept. Now let's see what is the real mathematical version. Coming back to pure mathematics, you just assume a function y which is a function of x, a variable x, where y is a function and x is a variable. Please do remember this x represents a variable. Okay. Now you have an equation like this function, and how will you expand this? You'll be expanding this equation with the help of Taylor series. And if you have a function y is equal to f of x, according to Taylor series, you'll be expanding like y is equal to f of x naught plus dou f by dou x at x is equal to x0 into x minus x0 plus so many higher terms divided by n factorial like that. So we are going to neglect all those higher terms and we are going to write only this much. Y is equal to f of x0 plus dou f by dou x at x is equal to x0 into x minus x0. Now, what is this x and what is this x0? X simply means variable. X0 means the initial value of that particular variable and x means the value of that variable at the present instant. Okay, so you can see the initial condition is actually represented by x0. Okay, so by rearranging this equation, you can write it as y minus f of x0 is equal to dou f by dou x at x is equal to x0 into x minus x0. For the time being, you just neglect what this at x is equal to x0 because we will be using this later. It has nothing to do with differentiation. So how will be differentiating is dou f by dou x of x minus x0. You can write it as dou f by dou x into x minus dou f by dou x into x0. So again you can write it as we are shifting this term to this side. We'll be getting y minus f of x0 plus dou f by dou x into x0 is equal to dou f by dou x into x. Okay. Now from this, what I want to know is this x. So how can you write x is equal to? You can write x is equal to dou f by dou x inverse into y minus f of x0 plus dou f by dou x inverse into dou f by dou x into x0, so that dou f by dou x got cancelled and here you got it as x0. Or I can write, this is our usual pattern, we understand x is equal to something, right? So you can write x is equal to x0 plus dou f by dou x inverse into y minus f of x0. Now without just simply writing these equations on equation, let's try to understand what is this equation. We know that x0 means initial condition. So you can say that x is a condition at the current state, isn't it? So I am introducing our iteration count. You remember our iteration count in Gauss-Seidel method. So here I am introducing our iteration count. I am writing it as x raised to k plus 1 is equal to x raised to k. That means x raised to k plus 1, if it's the present state, then you can say that x raised to k is the previous state. Okay? Plus dou f by dou x inverse into y minus f of x0, isn't it? So So I can write it as f of x raised to k. So this is one equation, or this is a pure mathematical background based on the Taylor series. Now with this, we are now going to compare this condition to our power system. So we have, I hope this much is clear to you. As per this, we can say that x is a variable and y is a function. Now coming to our power system, I can say that P is a function of voltage. Here for simplicity I am not representing modulus, simply V here means magnitude. Okay. So P is the function of V and delta. Q is also function of V and delta. So I can say that in a power system I have two functions. The first function is P and the second function is Q. Okay, I have two functions. That two function is P and Q. I can say that function 1 is P and function 2 is Q. Two functions are there. And how many variables are here? Is there only one variable? No, we have two variables here. V and delta are the two variables. So instead of a single variable x, in power system I have two variables V and delta. Instead of a single function f in mathematics, in power system we are considering two functions. One is P and another one is Q. Okay, now we are going to expand like the mathematical equation. Now, let's consider a system where the total number of buses is equal to n. Okay, and bus number 1 is a slack bus. Okay, so here it is specified as slack bus. Why? Because if it is a slack bus, do we need to calculate its voltage magnitude and delta? No. That means the V1 and delta 1 need not be calculated. Then, which are the variables to be calculated? Then the variables to be calculated as are what? Angle of voltage of the second bus, angle of voltage of the third bus, angle of voltage of the fourth bus, like that, angle of voltage of nth bus. Similarly, magnitude of voltage of second bus, magnitude of voltage of third bus, like that, magnitude of the voltage of nth bus. Here we need not calculate the magnitude of voltage of first bus and angle of voltage of the first bus and magnitude of the voltage of the first bus. Why? Because the first bus was slack bus. You need not calculate these values, and so you cannot consider V1 and delta 1 as the variables. Variables are those which are to be calculated. Okay. Now referring to our main equation, this was our main equation in mathematics. So x raised to k plus 1. So here there was one variable x, but in power system we have two variables delta and v. Okay, so how many deltas you have? Do you have any single delta? No, you have delta 2, delta 3, delta 4, like that. You have delta up to n. Similarly, you have v from v2, v3, v4, etc., v up to n. So I cannot write as a single variable. Instead, I need to write as a matrix, right? So I have delta 2, I have delta 3 raised to k plus 1, like that, delta n raised to k plus 1. Then I have v2 raised to k plus 1, v3 raised to k plus 1, like that up to vn raised to k plus 1. This simple. So this entire thing is actually our x raised to k plus 1. Clear? Now, what is this x raised to k? So if x raised to k plus 1 is this matrix, it is easy for us to write the x raised to k matrix, right? It was delta 2 raised to k plus 1, here it is delta 2 raised to k. Here it was delta 3 raised to k plus 1, then it will be here delta 3 raised to k. And like that is our next matrix. Now we have one crucial matrix here, dou f by dou x inverse. Now let that be like that. We will see to it later. Now, which all are the functions? We have mentioned that we have two functions, one is P and another one is Q. Now, is there any single P and single Q? No. Since there are n number of buses, we have P and Q from P2, P3, P4, like etc. up to Pn. and Q also from Q2, Q3, Q4, etc. up to Qn. We did not consider P1 and Q1. Why? Because first bus is slack bus. We can neglect all the parameters of a slack bus. So our count will be starting from 2. Clear? So y minus f of x raised to k. What is f of x? It is simply y itself. Okay. So y raised to k plus 1 minus y raised to k. So p2 raised to k plus 1. First function. Okay. Minus the same function with initial condition. Isn't it? Y is one function. This is also y itself with the initial condition. Similarly, P2, P3, etc. up to Qn, Q2, Q3, etc. up to Qn. Okay. So, the simple equation or the Taylor series in our mathematics has become a huge matrix when it comes to power system. Why? Because in power system we have so many variables and so many functions. Now we will see this percent, that is dou f by dou x inverse, and we call this matrix by the name, very important, Jacobian matrix, or represented by J. Okay, Jacobian matrix which is represented by J. Now you just observe here, it is dou f by dou x. How many f do we have? P and Q. How many variables do we have? V and delta. So what all may be the elements of this matrix? Yes, you can see here. It is, first function is P, right? And first variable is delta. So dou P by dou delta, one variable. Dou P by dou V, another term. And our second function is reactive power Q. So dou Q by dou delta, one term. Dou Q by dou V, another term. Since we have two functions and two variables, a single element in a Jacobian has now become a matrix with minimum 4 elements. Clear? Now, we will see to it now. Now we are going to write our Jacobian, our very big Jacobian matrix. Very big Jacobian matrix. Yeah. What about this? So, in our particular case, we have assumed that we have n number of buses. So, starting from the second bus, how many functions of active power do we have? We'll be having P2, P3, etc. up to Pn. And how many variables? Delta 2, delta 3 up to delta n, and V2, V3 up to Vn. So each function should be derived with respect to each variable. So which are the terms? Dou P2 by dou delta 2, dou P2 by dou delta 3. So each function should be differentiated with respect to each variable. So dou P2 by dou delta n, dou P2 by V2, dou P2 by V3, etc. up to dou P2 up to Vn. So with this, we have completed one single function, P2. Similarly, we have another function, P3, which again has to be derived in the same fashion. Dou P3 with respect to delta 2, with respect to delta 3, etc. with respect to delta n. Similarly, with respect to V2, with respect to V3, etc. with respect to Vn. Our second function is also over. Likewise, we need to do for dou P4, P5, P6, etc. and which will be our last term? Pn. Dou Pn by dou 2, Pn by delta 3, like that up to delta n. Okay, so with this, all our functions are over? No, only our active power functions P is over. Now our function Q is remaining. We also have reactive power starting from Q2, Q3, etc. up to Qn. So likewise, we'll be differentiating each Q2 with respect to each variable delta 2, delta 3 up to delta n, V2, V3, etc. up to Vn, like that. Okay, And likewise we have reached our last reactive power Qn, and our last element will be Qn with respect to Vn. Okay, and you observe this much term. These are all dou, we can generalize it as dou P by dou delta, isn't it? And this is called the first element of Jacobian, J1. And what about the second element of Jacobian? It is simply dou P by V. Okay, so it is the second element. And this is the third element of Jacobian, Q by delta. And this is the fourth element of the Jacobian, it is Q by V. Likewise, we have four main elements in the Jacobian, that is J1, J2, J3, J4. Okay, instead of writing this entire matrix, we have simplified the matrix like this. Clear? Now, instead of writing the entire delta, you have represented it as a single delta. We didn't put here 1, 2, 3 like that. Instead, we just represent it as delta. Similarly, instead of writing the entire V, we have represented it by a single V. Here also. Okay. Instead of writing the entire P, P2, P3, P4, etc., we have written a single P. Instead of writing Q2, Q3, Q4, etc., we have written a single Q. So this is a basic equation, or this is a main equation, this one. As a main equation we require for solving the problems in Newton-Raphson method. Now with this equation, we are moving further. That is, we are going to solve our first element, Jacobian J1. What was J1? It was dou P by dou delta. So we are simply, I means any arbitrary bus. Q can be any arbitrary bus. Okay. So we can write generally as dou Pi by dou Q, where Q can be any value from 1 to n. Okay. So what was P? We have, do you remember? We have already found out an equation for P. Yes, this was our equation for P. And this equation we are going to differentiate with respect to delta. Okay, so while differentiating, it is quite simple. With respect to delta, if I am differentiating, it becomes cosine of angle, it becomes minus sine theta or sine delta. Okay. So upon differentiating that PI with respect to delta, you'll be getting like this. Okay. With respect to delta, you'll be getting like this. You'll be getting sine of that particular value. You can just differentiate and see to it. Okay. And our second element was differentiating this reactive power with respect to voltage. That means we are going to differentiate this equation with respect to voltage VQ. With respect to VQ, you are going to differentiate. So this will be your equation. And J3, that is the third element in the Jacobian. It was the differentiating your reactive power with respect to angle. Reactive power with respect to angle means, again, it was sine of a particular angle, it became cos. We have a minus sign over here. And the fourth element will be differentiating the reactive power with respect to the magnitude of the voltage, and that is what over here. Okay, now you can see the different elements J1, J2, J3 and J4. Now is there any relationship between J1 and J4? Is there any relationship between this J1 and J4? Both looks same, right? J1 and J4 looks same, but In J1, you have an additional voltage term which is absent here. So you can say that J1 is equal to J4 with this voltage magnitude. So you can write like this: J is equal to Jacobian is equal to, instead of J1 you can write it as J4 into VQ, then J2. Similarly, while observing J2 and J3, you can see that J3 will be equal to J2 with a minus magnitude. Okay, so this is all about the mathematical background that we require in Newton-Raphson method. So in Newton-Raphson method, you should be thorough with the J1, J2, J3 and J4. What is J? How will you calculate J1? How will you calculate J2? How will you calculate J3 and J4? And the next thing you should be thorough will be the variables. Which are the variables in Newton-Raphson method? In Newton-Raphson method, the variables are magnitude of bus voltage delta and angle of bus voltage V. Similarly, which are the functions in the Newton-Raphson method? In the Newton-Raphson method, the functions are active power P and reactive power Q. If we have a slack bus, we will be neglecting all the terms, parameters associated with the slack bus. Okay, I hope this background is clear to you. And once you clearly understand the background of Newton-Raphson method, it is very easy to proceed with decoupled load flow. Very easy. Okay, so the main two assumptions in decoupled method as well as the fast decoupled method are derived from Newton-Raphson method. These are based on the modifications that we are incorporating in the Jacobian matrix. Because Jacobian matrix is a matrix which mainly determines the accuracy or the calculation in a Newton-Raphson method. So if you are modifying this Jacobian matrix, it would be if the complexity of the Jacobian matrix can be reduced, then fast calculation is possible. Okay. Now, for that, in order to make this Jacobian matrix more simple, some assumptions are made. First assumption is the real power or the active power P is mainly dependent on the angle delta and than its magnitude. So what does this sentence indicate? This indicates that the active power P mainly depends upon delta. It is independent of voltage magnitude. So you can say that dou P by dou V is equal to 0 because active power and voltage are not dependent. So it can be equal to 0. Okay. Similarly, another assumption is that the reactive power Q mainly depends upon magnitude of the voltage than its angle. So we can say that dou Q by dou delta is also equal to 0. So if dou P by dou V equal to 0 and dou Q by dou delta is equal to 0, which all terms in a Jacobian matrix can be equal to 0? Yes, these two terms in a Jacobian matrix can be equal to 0. So your Jacobian matrix become much more simple now. Same equation I am rewriting here with these two elements as 0. Okay, these two elements as 0. That is actually decoupled load flow. What do you mean by decoupled? You are decoupling something. What are you decoupling here? You have removed the couple between active power P and V, and you have removed the couple between reactive power Q and delta. So that has become decoupled and it has become equal to 0. That is a decoupled load flow method. Now I have moved this term over this side of the equation. So it becomes delta raised to k plus 1 minus delta raised to k. What is this? Delta raised to k plus 1 minus delta raised to k means what? Current value minus previous value, isn't it? Which is represented by delta delta. Similarly, V raised to k plus 1 minus V raised to k means what? Voltage of the current stage minus voltage of the previous stage, that is delta V. So it has become equal to J1, 0, 0, J4 inverse into this. Here also it is applicable, right? Instead you can write this delta P and you can make it as delta Q. So this is the mathematical background in decoupled load flow method. Now we are moving on to the fast decoupled load flow analysis. It is again quite simple because the fast decoupled load flow method is derived from decoupled load flow method. We know our equation of this decoupled load flow method. We have only two terms in the Jacobian right now to calculate. This was our first element that we have already calculated, and this is our fourth element. This is also calculated. Here, again some assumptions are made in order to make this Jacobian matrix much more simple, or rather much more simpler. Assumptions are angle of voltage in per unit will not differ much. So you can write delta I minus delta Q will be approximately equal to 0. Cannot say it is equal to 0. It is very difference is very less. So it can be approximately equal to 0. That means what? Here delta I minus delta Q. Here also there is one delta I minus delta Q can be reduced to 0. So it becomes sine of minus theta IQ. Here also it became sine of minus theta IQ. Okay. Now the second assumption was voltage of individual buses will be approximately equal to 1. That means if you are considering individual buses, it can be approximated to be equal to 1. So here we have VQ can be equal to 1. So this also term vanishes. So these two equations looks similar, right? J1 is equal to J4 like that. Equation looks similar. Now your equation becomes J1 is equal to VI YIQ sine minus theta IQ. Here also same thing. Now we will see this triangle, susceptance triangle. And here if this side is 1 by R and this side is 1 by X, then this side will be 1 by Z, which is nothing but our admittance Y. So you can see if this is an angle theta, you can see that Y sine theta is equal to this side, which is 1 by X. 1 by X is called by the name susceptance B. So instead of Y sine theta, I can write it as B. So instead of YIQ sine theta IQ, I can write it as BIQ. Okay. So you can write the Jacobian as minus BIQBI here, substituting this Jacobian over here. Okay. So that's it. This inverse. So in order to remove this inverse, I can write it as in order to remove this VI also, I can simply write like this. Okay, if I want to remove this VI, I have to multiply this, into this VI I want to remove, then it will become by VI over here. Okay, so the same equation, the modification here we made is, we have made some more assumptions to this decoupled load flow method, and we have finally derived at the fast decoupled load flow method. Okay, so in this lecture we have mainly covered the mathematical background of NewtonRaphson method, and mainly it is derived from the Taylor series, and in the power system point of view we have the variables as delta, that is magnitude of the voltage P and the angle of the voltage delta, and the functions included in the power system are the active power P and the reactive power Q. And based on these functions and these variables, we have derived from Jacobian matrix, which is a crucial matrix in NewtonRaphson method, or this is a matrix which mainly determines the final answer of by using this NewtonRaphson method. But since a large matrix is there for computation, it will be quite difficult to compute it with this very large matrix. So some assumptions are made to this NewtonRaphson method, and later on we derive to a new method, that is decoupled load flow method. Remember, in the decoupled load flow method or in the fast decoupled load flow method, modifications are done in the Jacobian matrix, and all these are done in order to simplify the calculation. Okay, so this much is about the mathematical background behind this NewtonRaphson decoupled load flow and load flow analysis. In the next lecture, we will be discussing in detail how a problem is solved using this NewtonRaphson method and fast decoupled load flow method. We will be working out one or two problems on that. So then this idea will be much more clear to you. Again, if you have any doubt on this, please feel free to contact me. Thank you.